Yeah, we left like. I got 2007.
Okay, so we're going to get started. It's my pleasure to introduce one of our new faculty, Platzer, here at Carnegie Mellon. Right now, he's an assistant professor in computer science. His specialty lies in deriving provable correctness for incredibly hybrids, developing algorithms and demonstrating that provable correctness for highly hybrid systems. He's looked at cars, planes, trains, automobiles, all sorts of things, and he's developed some groundbreaking provable theories in hybrid systems. Most notably, one of them is him being able to prove the correctness of a system without having to solve differential equations. And he calls those, I guess this will be in your talk, differential invariants.
Yes, that's right.
So instead of me going on and on bragging about what Andre can do, I think it's better if Andre tells us.
I'll brag. Okay. Yeah, thanks.
Thank you.
Okay. So I have to apologize right away for all this logic in the talk, but it's not like you haven't been warned. Yeah, it's in the title. Yeah, but the logic is not just there for the fun of it. I mean, I'm having fun with this, but on the other hand, it's really necessary in order to capture on a formally rigid and sound and reasonably well-defined way what this is all about. Okay, so kind of the ultimate question behind this is how can we build computerized controllers for physical systems that are guaranteed to meet their design goals? And the most important word in this for me is the guarantee, because of course a lot of people are building lots of interesting systems and they can achieve various wonderful tasks. But then for me the most exciting question is, okay, what can we do at all in order to ensure that we have some reliability, some guarantees that the system ultimately will do what we want it to do? This tunes right into the hybrid systems model, which is an increasingly more prominent mathematical model for systems with both a continuous and a discrete dynamics. Well, the continuous dynamics, for instance, in a train or a car or a robot or whatever, of course, comes from the movement. So maybe the position is evolving, and of course that one is evolving continuously over time. And the position would be evolving continuously too, but other control variables in the system are evolving discretely. So for instance, the acceleration of the system is evolving discretely. So at discrete instant, we change our mind about what we want the acceleration to be. Now, if you take one step closer, it actually wouldn't look exactly like this necessarily, because of course, even the acceleration, I won't necessarily be able to change from 2 for acceleration to -1 for braking, like instantaneously. That doesn't necessarily exactly work like this. But on some level, it's a very good approximation. Especially on some level, my system will reach a discrete decision and say, now I decide that I want to brake or accelerate, or now I decide that I want to go left or right. And then the hybrid systems domain is sort of the systematic static of systems that have both continuous dynamics and discrete dynamics, where the continuous dynamics you would typically describe by a set of differential equations, and the discrete dynamics by some control. Okay, so first of all, the study of these systems is of course more than computers, because just because you prove that there's no null pointer exception in your code, that's a good start, but it still doesn't mean your train will be safe or your aircraft cannot crash or something like this. It's also more than physics, because if you just sit down and think about the physics and, for instance, derive a reasonable braking control law for the system, then you will find that even though it looks promising, the system still isn't quite safe. And the reason is, well, if the system is hybrid, so the system has both continuous and discrete parts in it, then the way to understand it will also have to have some discrete and continuous parts in it. Especially the joint dynamics requires a constraint, something like this, which from the physics alone you will not get. And where does it come from? Well, for one thing, in this example, it's fairly easy to see where it comes from. If, for instance, this is, let's say, a controllability region of your system, so velocity, time, and then the move and authority in the train scenario is rather easy to see. It's the last point on the track up to which you're allowed to drive to. No further, because there could be other trains beyond. And within this region, your system would in principle be controllable. And at every point in time, you have a decision, do I want to accelerate now, or do I want to brake now? Or degrees of this decision, how strongly do I want to accelerate or brake? And if at this point you are inside, so in the interior of the controllability region, it looks tempting that you would be able to accelerate. The unfortunate truth is that that's not quite the case, because if you start accelerating now, you may be stuck with this decision for a little while. And contributing factors, which shouldn't be any surprise to you, are of course that sensor information isn't available continuously, even though we might think it is, but it's not quite right. Computing in order to reach a decision takes a little bit of time. And worst of all, the actuators are not necessarily always instantaneously able to act. So if we decide to accelerate now, in the good scenario, we may have a chance to react to this decision later on. In time, in the bad scenario, we will not. And then, of course, even if we then perfectly brake, we're going to miss the movement authority point. So there's lots of, well, let me say just informally, cofactors determining from the movement authority, velocity, position, and so on. Lots of influences on this design parameter of the start braking point in your system. And well, what you got to do is this, but how would you know? Yeah, how would you come up with something like this? And more generally, and this is where the logic comes in, more generally what you want to know is what is the constraint, yeah? And first step even, am I asking the right question about my system? What I want is for all movement authorities that are somehow given to us externally as a parameter in the system, there is a start braking point, well, that we can play with, such that the train is always safe. That's the logical formula we care about. And much of the study behind this is making this formally precise. Why is this a logical formula? Yeah. Let me, in the interest of time, just skip over this comparison. And just make one point why the hybrid systems domain is a little more tricky than most people think. So suppose you're given a continuous evolution of the system, and what you want to do is decide if you ever hit one of those terrible bad states where you have crashed with another vehicle, for instance. Well, and suppose what you want to do is just decide this naively by evaluating this model of a system at various discrete points. Okay, so you may say, let's check here. Point looks good. Maybe let's look at the derivative. Point looks good. Okay, let's check here. Point looks good. Derivative looks good. Maybe something in between goes wrong. So let's check here. Point looks good. And at some point, if you have a decision procedure, it would have to stop with this point-based evaluation at some point. And now the only unfortunate part is that if, for instance, in this scenario, it would come up with the answer, yes, system is good, you can crash, then unfortunately there's another behavior of a system which looks exactly the same at this point, including all the derivatives, exactly the same here, exactly the same here. Only one of them is unsafe, the other one is safe. So whatever you're trying to do with deciding this numerically, it just doesn't quite work out. So that's a very simple way to see that you have to be much more careful with this. And more generally, this, well, image computation problem, or the problem of when I follow this dynamics of the system, will I ever get to a bad state or not, is even already undecidable using numerical evaluations like that for arbitrarily effectively given flows that are arbitrarily smooth on effective domains. And worst of all, even if you tolerate arbitrarily large errors in your decision, if you say, okay, I don't care if I'm a mile off with my decision, yeah, but then I will really want to know. Still doesn't get you anywhere. Yes?
Quick question is the notation. What's B and what does it mean for D and E to be effective?
Yeah, okay, this is kind of computability theory over the reals, really. Yeah. But you should think of D to be the domain of your system.
Right.
So for instance, if you have something like, okay, but I know my velocity is always greater or equal to 0. I just don't care what's beyond that. And B is kind of the good or bad region that you care about. In this scenario, it's the bad region. And, well, if they would be given ineffectively to you, you can't do anything with it. Yeah? But even if you assume very friendly assumptions, like everything is effective, everything is arbitrarily, precisely computable, and so on, still the very question itself is not. So that's a bad way to start, even though this point-based evaluation may be the first way to start. Making sense? Good. So hybrid systems analysis occurs everywhere and is important everywhere. So cars, trains, aircraft, reactors, medical devices, and as you should imagine, lots and lots and lots of robotic applications. Now, the first thing you need in order to be able to have a formal way of talking about what your system is, so what's the model of a system, and what you expect it to do. You need some way of saying, everything that my system will always do will be safe. How do I say safe? So the first thing you need is some logical language to characterize what you want your system to do. Well, and what I've come up with is this differential dynamic logic to do the job, but let's take it step by step. So first of all, you need to be able to talk about variables over the reals, unsurprisingly, because your system has real positions, real velocities, and so on, so you care about those. And you immediately start caring about nonlinear constraints, because if you just have a linear way to talk about the variables, you're going to miss all the excitement, or you're going to miss, for instance, that this actually is the right answer for the controllability region of the system. Good? So you have real arithmetic as a basis. And what you also may have to do is, for instance, oh, and I care about my velocity not being too high. And you may care about, of course, both at the same time. So you care about the logical conjunction of my velocity isn't too high and this other constraint on the relationship. You may also, of course, in other scenarios, care about disjunction. So you need at least all propositional logic and nonlinear real arithmetic as a basis. But that alone is not enough, because you need more. What you need more is quantifiers, for instance, in order to be able to talk about, for all movement authorities that, for instance, in the European train control scenario, the radio block controller would provide to us, which is an external parameter as far as the train is concerned, but an internal parameter as far as the radio block controller is concerned. And you want to say something like, for all those choices that could be imposed upon us from externally, there is an internal choice for the start breaking point, such that blah, 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 blah. And you also need quantifiers to talk about time. For all times in the future, something holds true. So the logician would stand up and say, okay, what you need is first-order logic interpreted over real numbers. But unfortunately, that ain't enough, because so far you can talk about what's going on at one state of the system. Yeah, you can have a formally very precise way of characterizing when, for instance, your current state would be good or bad or safe, but you do not only care about what's going on at one state of the system. Of course, you care about what's going to happen all the times in the future. So what you need is some logical way of saying this logical formula holds always. And, well, that's what logicians came up with as this box modality. That means, for those of you who have seen linear temporal logic or CTL, for instance, it's very similar. That would mean always, in all reachable states, the safety property that I care about will be true. Now, the always we need to qualify by always when. I mean, always when what happens. Yeah? So the way you do this here is that you say, always when I follow the train dynamics. So you're going to parameterize the box by a train, for instance, and say, always when I follow the train, the formula will be true, meaning in all reachable states of the system that I can get to by following the train dynamics model, I'm going to be in a safe state. And that's good, because this is exactly what you care about. Now, for the train, of course, so far you haven't won anything, because you still need to say what your train really does. How does it evolve over time? And the least thing you need for that is a differential equation in order to describe this is how the system is evolving continuously over time. On top of that, you have some control. The easiest example of a control would be, well, if my position is more than the start breaking point, so we're somewhere here, then I set my acceleration to minus b for braking. And after I'm done with that, I'm going to continue with the differential equation. And the whole thing is a logical formula. And what it means is always, this is what the funny square brackets are for, always when I follow this dynamics of my system, the formula down here will be true. So no matter where I go when following this dynamics, the safety property will be true. And of course, if you now stick your favorite system in the box and express something like the position to the other train is good, or my velocity for an aircraft. The velocity of my aircraft is not too small, otherwise I'll be stalling and things like that. Then you at least have a reasonable way to express what you want to say. And this, by the way, would be an example of what is called a hybrid program. You think of a hybrid program as a standard program you use all the time anyhow to program your system, except that in addition, what you squeeze in are those differential equations that you want in order to be able to describe what happens over time when you just let your system flow for a certain period of time. Okay, now it also could make sense to just use a graphical notation for the same thing, so an automaton-like notation. For instance, for the train, you could have something like, first I'm far away, then I come close and start negotiating with the other train. Depending on how it works out, I either go into a correction mode, and then when I'm far away again, I'm going into far mode. Or if it doesn't work out, I'm going to go into a recovery mode, and finally I'll be in a fail-safe mode. Or something like this, plus lots of differential equations and switching and conditions and so on attached to this. This also might make sense. And of course, you can define a logical notation for that, which would be, well, all behavior of this graph notation for my system satisfies the safety property. The reason why I've chosen the hybrid program notation and favor it over the hybrid automaton notation is not just because this is terrible to write down, but more importantly because the next thing that I'm doing with this is not just to write it down, but do reasoning with it. So verify properties like this one. And how I want to do this is take this logical formula and prove it by looking at its parts. And if you look at the part of this logical formula, what you would want to do is, for instance, pull out the negotiation phase into a separate logical formula. And then what you have here is nothing anymore. Yeah, it just, and when I'm done with the far mode, the world ends. Yeah, that doesn't get us anywhere. Yeah? So formally or from a logical perspective, this is what makes automata model like this hybrid automata model not compositional, so that's why we can't use it for our purposes. But what we can use is this hybrid program notation, where you just add a differential equation as a primitive operation for continuous evolution on top of standard programming constructs. Now this is kind of a logical essentials point of view of what you want as a programming constructs. Of course, in reality, you need lots more. But you can define all of them with just those few, which is why I didn't bother writing the other ones down. So you have differential equations. You have a discrete jump for assignments. We have, for instance, an if and else for doing conditional execution. You test the center variable, and depending on how it goes, you're going to do alpha or you're going to do beta. You can do sequential composition. So first, I'm going to do alpha, and then when my system is done with it, it's going to continue according to beta. And then you can do a non-deterministic choice, so meaning either I do alpha or I do beta. And that's, of course, a little unusual as far as programming is concerned, because you don't really seriously want to program into a robot non-deterministically. You know? Toss a coin, go left or go right. On the other hand, your environment model is extremely non-deterministic. And since what ultimately you're interested in this is modeling your control that will follow the various opportunities that the environment provides to you, follow the dynamics and so on, there's going to be some non-determinism in it because you just can't quite know if someone comes in through the door right now or not. So you have to sort of consider both options, and that's where non-deterministic choices come in quite handy. The other logically fundamental feature you need is non-deterministic repetition, because so far everything is flat, straight line code, no loops, no nothing. But as soon as you add an operation saying, well, now this process that describes my controller and my dynamics and so on is a process which, of course, repeats over time as often as it wants. So, example. This is a still simplified example for the European train control scenario. And notice the canonical pattern here. First, my controllers do something, then I drive for a certain period of time. And this is a process that repeats, which I indicate by this regular expression style star operator for repetition. Okay? How do I characterize the control? Well, if blah, blah, blah condition on my start braking point, if this is bad, then I'm going to have to set my acceleration to -b for braking, and otherwise I'm going to set it to something else. I actually want to accelerate. Or I'm going to have lots of choices. Or I'm going to follow a PID controller or something. It really doesn't matter too much for the purposes of this. And then the driving is a simple differential equation you've already seen, except that you add some bells and whistles to it and say, OK, maybe I also want a time variable, which is nothing more fancy than just time evolves with derivative 1. Well, who would have imagined something like this? And this control, plant, and repeat pattern is something that comes up very naturally. This is only a simple example, of course, but the other ones don't fit on the slide. OK, if you have your dynamics of a system and your control of a system captured in some way, then the next thing you can do is, for instance, write down those logical formulas using, well, propositional logical operators, quantifiers, arithmetic, and most importantly, the box and diamond modalities. So for arbitrary hybrid programs alpha that describe your system dynamics, and arbitrary logical formulas that describe what you want to be true in the states that you reach, you're going to have this alpha box phi and alpha diamond phi logical formulas. And the alpha box, that one means always, when I follow a system, every single state that I see will satisfy the phi formula. For instance, here, if a condition on my start braking point is true, then always, when I follow this dynamics, my position will be within the movement authority bounds. And that's, of course, good, because think of this picture. If all the trains are within their local movement authority bounds, and that one also is, and so on and so on and so on, then if the radio block controller makes sure that at every point in time the movement authority regions are disjoint, and every train keeps within its movement authority region, then the whole system is collision-free because trains can never crash. And that's, of course, exactly what you want. Now, just to briefly mention, the alpha diamond phi would be the dual. Alpha box phi says always when I follow alpha, the system is safe. And alpha diamond phi means I can follow the system. If I just wait long enough, I'm going to see the phi state. OK. Just briefly, assignments will correspond to jumps in the state space. So think of this as time, and then the assignments are going to be a jump. Well, differential equations will correspond to a continuous evolution in the state space. Skip that. Sequential compositions would be, well, first I do alpha transitions, and then I do beta transitions. For instance, first I do a continuous evolution, and then I do a discrete jump. For the continuous evolution, I didn't say how long exactly it's going to take. It's non-deterministic. Yeah? It could be an hour, it could be a second, it could be half a second, it could be anything. So this evolution overall could take longer or shorter. And both of them are possible. And this is important in the verification because in reality, you do not know exactly how many milliseconds it's going to take until your controller is going to do something again. If you take a look at the system and analyze it under the assumption it's going to be exactly half a millisecond until my controller does something again, that's good, but the trouble is, what if in reality when you run it, it's not quite the case? So you have lots of non-determinism here that you better take into account. Well, and the repetition just corresponds to you repeat the process. Yeah, so you do, for instance, continuous and discrete and continuous and discrete and continuous. And this is where you see why it's really called hybrid, because parts of your system evolution will be continuous, other parts will be discrete and can be mixed rather arbitrarily. Skip about the rest. Okay, now after I hope you see that with this you can capture dynamics going on and control going on, the next thing I want to do is specify the properties and prove the properties, and prove properties by talking about parts. Well, if this is a continuous dynamics of your system, it actually happens to be a damped oscillator. And this is one mode your system can be in. And this is another mode your system can be in, another damped oscillator. So here's the two modes of your system. And someone want to reason, well, both of them are safe. Maybe both of them are contained in this box. Yeah? So if I put the systems together and switch between them, obviously they're also going to be safe, right? I just compose two safe things. Yeah? So let's do some switching. For instance, you switch at the diagonals. So you're going to start here, and when you hit the dashed line, you're going to switch to the dashed mode. Go here. When you hit the solid line, go to the solid mode. Go here, hit the dashed line, go to the dashed mode, and so on 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 and so on. So obviously, the system is still safe in the sense that if you start within this box, you're going to stay within this box. This is good news, because safe plus safe is safe. The only trouble is that this doesn't work, because if I switch slightly differently, if I switch here instead of here, then I'm going to do the same thing. Start, evolve, switch, evolve, switch, evolve, switch, evolve, switch, evolve, switch, and so on and so on and so on and so on and so on. So my system eventually is going to blow up. It's going to be incredibly unstable. And particularly, it's not going to be contained inside any of those boxes, because if I just wait long enough, all this stupid switching will have killed the system. So in order to get this philosophy of checking a whole system by checking parts to work out, you're going to have to be careful, and you're going to have to put some logic into the whole thing. But that's what you see now. So in logical notation, if you care about after you've done a discrete jump by an assignment, after that you're safe. Pictures, this would correspond to if I'm currently in this state, do an assignment, then I'm safe. And if this is the property that I want to prove about my system, well, then I can prove it in very simple ways, because I just show that before that, the system has already been safe, just with the new value theta inserted instead of the old variable x. So for an assignment, reasoning about if it's safe, I just have to carry out the assignment, essentially. That's good news. Now for a differential equation, if I care about I can't follow this differential equation to a point where the whole thing is safe, or I've reached my goal, then, well, what can I do? The easiest thing I can do is just say, OK, I have a differential equation. Maybe I can solve it. So let's get a solution of this differential equation, more precisely a solution of the initial value problem, which actually happens to be a symbolic initial value problem, not a numeric one. Then you can say, OK, if I have a solution, then all I need to ask is there a time t such that if I insert time t into the solution and then make it jump instead of continuously flowing around here, and if I then hit a safe state, of course, my differential equation is going to be able to do the same thing, just continuously follow it. The only trouble is with this approach that you narrow your attention to a very small class of systems, because when can you hope for a solution of a differential equation? Well, not too often. But OK, just have a little patience. We're going to get there. Now, the good news is that everything is compositional. So for instance, if you want to show that all behavior of a system that can do a choice between alpha and beta is safe, all you need to do is prove that all the alpha behavior is going to be safe, which is the left formula here. And completely independently, separately, all the beta behavior is safe, which is the right subformula. If you've proven them both, then you also know that a system that can do arbitrary choices between the two will be safe. And this is where this compositionality comes from. You have one complicated system and a property about it. And reasoning about complicated systems is tricky, so you say, let's reduce it to lots of questions about simple systems. And that's something you can then do. And that's also something that in the actual verification and so on gives you lots of scalability benefits. I'm going to skip over that. And just briefly mention for a repetition, what you use is an induction property. So you want to show that when you repeat alpha, you're safe. And instead, you show that whenever you start safe and do just one step, you're going to be safe. Because if you then start again, you're safe. Do another step, you're safe. Do another step, you're safe. Do another step, you're safe. So this is just like induction in mathematics. And for differential equations, you can actually do the same thing. You can take a differential equation and define the induction over differential equations, where you have a slightly different notion of what it means for a logical formula to remain true when you follow a differential equation, which formally is defined in terms of total differentials and substitution, blah, 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 blah. But the intuition is you have a property that remains true when you follow a differential equation system evolution. And that's precisely those differential invariants that Howie talked about earlier. Now, because I want to go to some, I'll give you a little bit of an overview of various applications and so on. I'm not going to talk about too much of the details here, but the intuition is, if this is the vector field of your differential equation, so essentially plot the right-hand side as a vector, then a solution, a global solution of that would correspond to this curve. If you start here, blah, 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 my f curve is going to go here, blah, 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 blah. If you are interested in safety verification, so for instance, your safety property is you're never going to go into one of those bad blue regions, then of course, you can answer this by looking at the solution of your differential equation. Essentially, what you have to do is start your solution at every possible initial point, blah, 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 blah. Check at every possible point along the differential equation solution that you don't go into a bad blue region, and then you're done. The only downside is that's a lot of work. The more serious downside is usually this is exactly the problem that's undecidable, as we've seen in the beginning with this numerical point, evaluation point. So this is something you can't quite do. On the other hand, that's not what you care about. You don't want to know where exactly you will be going over time. All you care about is, could this possibly be somewhere unsafe? Or do you know that it's going to be safe? And for this question, all you care about is there any of those vectors pointing to where the dynamics is going that goes from safe into unsafe? If there is, you could be in trouble. But if there's not, if all the vectors are always pointing safe, 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 then you know if you follow those dynamics, you can never go somewhere unsafe if you only start safe. And that's good enough, because then you can look at your aircraft and show, I'm going to start safe, so I'm going to end safe. You will not be able to prove that this will be Paris where you land, but you know that it's going to be somewhere safe, and that's good enough. And this is the intuitive idea behind those differential invariants. Formally, you need some differential algebra and lots of things to get this right. Because the intuition is good, but there's some catches if you're not careful. So in order to get this reasoning sound, you have to be a little more careful, but that's the intuition. So if the solid region F is the safe region of your system, then differential invariants capture this. If a dynamics always pushes you towards the formula getting more true, so to your system getting more and more and more safe, then you're on the safe side. If, on the other hand, your dynamics pushes you into unsafe, you never know what happens. OK. Just because I want to briefly show how all this crazy logic fits together, what you can do, for instance, is start with a conjecture saying, my system, if it starts within the movement authority, then can I break, this is the breaking differential equation, and still leave the movement authority? And in order to find out, all you do is use the proof rules you've just seen. So start with this complex thing and take it apart. Go a little step. And now there's one extra bit that I haven't told you anything about, and that's the other reason why I'm bringing this up. There's those quantifiers inside. Quantifiers, OK, what do we do with those? Sounds like they might be tricky. The good news is that those quantifiers are over real variables. Real variables sound like they would be terribly complicated, but the good news is they're actually not, because there's a famous result due to Tarski from 1930, old. So that shows that quantifiers over reals can actually be handled. The only trouble is here you don't have anything like that. So you're going to have to do a little bit extra logic, say, okay, how do I get the quantifier away? Go over here, do some proof rules, go back, and say, oh, I have a quantifier over arithmetic, so now I can get rid of it. Okay, lots of logic being done. Then the good news is you have something at the end that characterizes exactly when this formula will be true. Because indeed, if you start within the movement authority and break, you can still leave the movement authority if only your initial velocity has been too high. And that's an example of, well, I want my system to be safe, yeah? I just conjecture it is. Do a couple of logic things, and ultimately I'm going to find out either true, so yes, it is safe, or I'm going to find out one of those constraints saying, yeah, it would be safe if only I would know this. So the thing to do is take this, and build it into your system as one of the assumptions, and just try again. Chances are you're going to find something else that doesn't quite work out. So you're going to take this into your assumptions and try again. And this is exactly what works rather well in practice. OK, this is theoretically completely exciting, but I'm going to skip over it. And instead show you what can be done in this area. For instance, you can verify quite a number of interesting properties about train control. You can prove, for instance, that your trains don't crash. You can prove that your trains nevertheless can reach any position on the track, and so on. Your model is, I mean, that's the problem. Yeah? If you prove that your system is safe, it might be safe because it doesn't move. Interesting mathematically, but practically completely useless because you just managed to indirectly over-constrain your system in strange ways. So in addition to, let's first get the safety right, the next question is, does it still move? And of course, a simple test is if you simulate or implement or build or run the system and see if it moves. Mathematically with that, you still won't know if it will always be able to get where you want it to go. So the other dual question is one of aliveness question. Will I always be able to move to every point on the track? If not, if I could deadlock myself somewhere, then I may be in trouble and so on. The approach also works rather well for air traffic control. So if you have a couple of aircraft that are flying on colliding routes, actually, you know what? Maybe I will just. So this is a scenario where the aircraft are flying and the air traffic controller didn't pay attention. The pilots didn't pay attention, which is OK because there's really way too many aircraft up there already, and we want to put more on. And then for this system, what people have done is, OK, let's just have some collision avoidance added on top of that. How about emulating the same thing that goes on the ground in traffic circles? So the aircraft go around in circles like this. Notice this peculiar jump here. Yeah? The aircraft go in this direction, and all of a sudden someone says, no, please do an instantaneous right turn. And they jump. Yeah, and go. Pilots might be scared about this, but nevertheless, this is one of the systems that people have proposed about 10 years back. It's the roundabout control maneuver as one of the ways to get around any collisions here. And it may look OK, yeah, but unfortunately, the verification shows that it's not. Because there's this scenario where you follow exactly the same principle, go arbitrarily. If you come too close, you do a right turn, follow a circle, and boom. Yeah? And that's, of course, precisely what you want to know before you implement the system, that something like this could happen. In order to fix this, first of all, you want to find this problem. But once you've found this problem, the next thing you want to do is fix it. And then you get into trouble, because this is how your differential equations look. Yeah? Cosine, sine, blah, 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 blah. And you say, maybe I look at it by solving the differential equations, and you get a solution of the differential equations. And the problem is not just that you stare at it and it's rather big, but the problem is that arithmetically you are in trouble, because what you want to know is ultimately if a logical formula characterizing a distance of the aircraft is true for all times in the future with this arithmetic expression just for the x1 variable over time, and similarly terrible things for all the other variables in the system. And that's just still a complexity argument. But the real serious problem from a logical perspective is here you have a quantifier and a cosine and a sine. And now a famous logician, Gödel, in 31, again a while back, has shown, no, not really, but has shown something that has a corollary that this is an undecidable problem, not even a semi-decidable problem, so you're really in trouble. And that's precisely the reason why instead what I've come up with is this differential invariant business where you can actually do things like that nevertheless. Now, remember those peculiar jumps in the beginning. I mean, it's nice to find a problem with that. It's nice to prove that you can fix the problem somehow. But still, if you then implement this maneuver in reality, yeah, the pilots are still going to be unlucky. So in order to get around that, what you can also do is sort of take the same principle but smooth out the entry procedures. So you're going to say, OK, let's follow a right circle, and then let's follow a left circle. And then when we're good to go in the original direction, let's just go straight. And a procedure like this, for instance, can also still be verified. It's just more complicated. So you agree, then you enter, then you go around the circle, and then you exit. And at the end, during the exit, you're still obliged to go straight on, because if you turn back right away here, then you may be in trouble. Yeah? But if you exit for a certain period of time, and then your distance is good again, then you go back into free flight where the pilots can do what they want, left, right, up, down, whatever, and so on. So there's a lot of things, a lot of different systems you can verify this with. This. Car control is another scenario that can be verified rather well. But because I want to give you some time for questions and so on also, let me stop here with the overview being, well, differential dynamic logic is a formal notation for hybrid systems characterizations of your models, of your systems. And what do I want? Do I want safety? What's the property? Do I want liveness? What's the property? Do I have 10 questions about the system and so on? I just write them down. And kind of the picture to keep in mind is this alpha box phi thing, which is central, where the alpha is the system that tells you in which direction does your system evolve over time. And the phi is the logical formula that you claim is true all the time at every single state you reach. And if this is the property you can prove, then you know that you can rely on, well, for instance, my safety property being true about my system all the time. Now, there's lots of logic for hybrid systems, lots of compositional proof, which are useful extremely for scaling up to the systems that I talked about, because they are at least one order of magnitude more complicated than you could do without the compositionality. There's theoretically exciting soundness and completeness results and so on. Differential invariants are a very interesting concept in order to scale beyond the rather simple and primitive differential equations that you can solve. And there's an implementation in this KeYmaera verification tool that will guide you through the verification process. So you can both kind of, and actually maybe I could just briefly show it. Let me just see. What do I need to do? You can both sort of, I have it online somewhere. Because, of course, proofs are great, but you don't want to have to do lots of manual handwritten proof like the ones I did on the slide and so on. You want to have some support for conducting proof like those. And that's what the KeYmaera system is for. Given the incredible speed of my laptop, I probably should have started before. Let me just bring up, while this is loading, let me just bring up one more point. The whole thing does not just work for hybrid systems, but it also works for extended systems, for instance, distributed hybrid systems, because hybrid systems is about one car. Yeah? In one car, you have continuous dynamics. In one car, you have discrete switching. In one robot, you have continuous dynamics. In one robot, you have discrete switching. But if then you have the gigantic network of them, lots of cars driving, or lots of robots swarming through the building and talking to one another, then it's not clear how the verification would scale up to that, because it's going to have an incredibly huge state space, dimension-wise. Yeah? And then the distributed hybrid systems is a fairly recent direction that captures this as, okay, there's lots and lots of robots, lots and lots of cars, but really all of them are, or lots of them are the same. So I have n cars or n robots in my system. And then with this distributed hybrid systems approach, you can still nevertheless prove interesting properties. Like, for instance, you have a string of cars driving on on a highway, maybe switching between lanes and so on. Nevertheless, the cars will never collide because the distances are always good. Okay. So, for instance, this is just more or less the most simplified version of something that has something to do with train control that you've seen from the slides. Of course, it would be more interesting to look at the real examples, but then I'm going to run out of time explaining them. I bought a new laptop, so I'm not used to this speed anymore. Here we go. Okay, so you have something like, here's the property. In the beginning, this is where I start. So my initial velocity isn't too bad, and my braking force my braking power had better be positive, otherwise it's hard to control anything safely if I don't have any brakes. My maximum acceleration should at least be greater or equal to 0. Then always, when I follow the system dynamics, I'm going to stay in this region where my position is within the movement authority bounds. And then the dynamics is something like, I'm going to adjust my start braking point, and then if my relation to the start braking point is bad, I'm going to be forced to set my acceleration to minus b for braking. Otherwise, I'm going to accelerate or do lots of more fancy things. That's also possible. And then down here, I follow the differential equation. And at the end, there's the star that says, OK, I'm going to repeat the whole process over and over again. And two ways of working with this verification tool is either for learning purposes and for helping out and so on, and manually, where you say, OK, I have some variables that I want to eliminate. I have an implication that I'm going to pull over to the left-hand side. I have a conjunction that I will split, and so on. But that's, of course, the way to learn the system and to help out and so on, but not the way you really want to use it. The way you really want to use it is just to say, OK, play. Go ahead and find me some proof for the system. So what the computer will do is take a look at the system and follow all those decompositions that you've seen. Okay, quite frankly, you've only seen one of those decompositions. Then it will try to find a proof here. It did find a proof, so property has been proven successfully. And you can look at, OK, what did it do? Property of this, it's a loop. So what it decided to do is induction. Here's, for instance, the induction step. What did it do? There's an if and else. Well, all behavior of an if and else is safe. Well, that could be two things. If my condition works out, I have to prove that it is safe. And if my condition does not work out, I also have to prove that it is safe, and so on and so on and so on. Do something with the differential equations, have lots of arithmetic at the end, and verify it. That's the kind of working with this KeYmaera verification tool. And I guess, let me just check. In order to get this to work internally, this logical analysis of hybrid systems, you actually need to combine lots from everywhere. I mean, there's lots of logic inside. There's theory improving, model checking, proof calculator inside. You need lots of continuous math, algebra, computer algebra, algebraic geometry, differential algebra, dynamical systems theory, lots of algorithms, like what's the right proof strategies, what are the decision procedures to use, what can we do in terms of fixed point loops. But then if you combine all of this, you can actually combine it into KeYmaera and hopefully have something that is useful for systems verification, in particular also for robotic applications. With that, I'll be looking forward to further questions about this. Thanks. Too much logic, I know.
Can you point to particular, say, train accidents where if they used this stuff to verify on software, would it happen?
Interestingly, with trains, that's not quite the case, even though there have been a couple of train accidents, unfortunately. They have been due to reasons of not even having a safety system in place. So what does it help if you verify a safety system that they then don't use? But for the air traffic control scenario, for instance, that's something that happened and was quite useful, I think, because the system that I've studied, this roundabout thing, is something that they had proposed for the next generation air traffic control system. Fortunately, they have an extremely careful and slow process. So even though it has been proposed 10 years ago, it's not like it has been implemented up in the sky already. And that's why, fortunately, my verification came in time and made sure that, okay, how about not implementing the system? But if you implement something like this, let's rather fix it, because here's the proof that you can rely on it and so on. Yeah.
I don't know if you're familiar with what goes on in autonomous vehicles, but I think in a way you have some of the inputs you have are a continuous cost map that defines your world, which is almost infinitely variables. Okay, something along those lines. And then you have also possible start and goal that are almost infinite possibilities. Are we at a point where we can formally verify a system like that, or something else has to happen before you can do that?
Well, all verification is a challenge. But this is one of the challenges that to some part has been overcome at the protocol level already. And so some part of it has been successful at the protocol level already, so I don't see a reason why we shouldn't try exactly this. And actually, I am involved in a couple of projects that do study the autonomous transportation domain. And one of the most important features is that you're really not, I mean, yes, you can think about this, that's great, but really the problem is this, lots and lots and lots and lots of cars. And that's exactly where the system model that you care about is not this isolated box in the corner of a hybrid system with lots of rather complicated and fancy continuous and discrete dynamics going on. It's really being embedded everywhere, being embedded in other cars driving on the street, being embedded in some car-to-car communication technology that will send some packages back and forth. And if you base your control decisions on what kind of information you receive, what kind of information your sensors get, you better make sure that the whole thing can never go wrong, sort of. And we have a couple of very interesting verification results precisely for this scenario already. But I'm sure there's lots more that also need to be considered in this direction. Was another question?
So modeling error is very important, particularly for the continuous dynamics.
Yeah.
My car starts to shake when I hit 70.
Okay.
And the same model car that someone else owned doesn't. And I didn't see how to deal with that. It introduces correlated error, so you can't simply model it with a noise source. So how am I going to verify my car if I can't get a handle on the variations that cars might have?
Very good point. So let me just generalize it a little bit and say the differential equations that I had to look at for air traffic control, these are the standard canonical differential equations you look at for answering questions about the general protocol layer behavior of aircraft. So they are accurate. Okay. On the other hand, if you zoom in a little more, there's also the actual aerodynamics and so on. That's a